This is the second part of the video on function approximation on subdomains. If you haven't watched the first part yet, please go and watch that part first, then continue watching this video. Alright, now I'm going to show you what is the answer for this part. So if you do the calculation properly, this is going to be the final answer. And this is going to be the shape of the approximated function. So the approximate function in the first subdomain was defined as 1.76x minus 1.24. On the second subdomain, from negative 0.5 to 0, is defined as 4.24x. And if we continue approximation, on the third subdomain, from 0 to 0.5, is the same as the second subdomain, and on the last part is similar to the one that we had in the initial domain, with the difference that here we had negative sign, but on the fourth subdomain we have a positive sign. So this one represents how a function could be approximated using linear element on subdomain. Comparing the accuracy of the approximation using 4 elements versus 1 element, it is clear that using 4 elements increased the accuracy. Those 4 lines are going to represent that exact function better. This way, the accuracy has increased by using more elements. This method is known as H approach, or mesh refinement approach, because we have increased the number of collocation points, we have refined the mesh, and by that we increase the accuracy. Now let me compare the accuracy of the H approach, or the mesh refinement approach, versus another method in which we increase the degree of polynomials, which is known as the P approach. So consider the same function as we had before, 3 sine of pi x divided by 2 defined over the same domain from negative 1 to 1. If a one-order polynomial is used for approximation, this is going to be the approximate function. Also, we have solved this problem using 5 nodes or third-order polynomials. In that way, we have seen that the accuracy of the approximation increased significantly. Now let's compare these two approaches with each other. In the H approach, we use the same element, the linear element, but we increase the number of elements. In the P approach, we use 1 element, but increase the degree of the element, increase the power of the polynomial used in the approximation. By comparing the accuracy of these two approaches, it is obvious that the P approach, or using higher order polynomials, is going to give us much more accurate answer. But higher accuracy is not free. Let's compare these two approaches together. In the H approach, or the mesh refinement approach, 1 element is used for the entire domain, and the accuracy is simply increased by using more elements. The main advantage of this method is that it is much easier to program using computer. On the other side, the accuracy of the approximation is not that great. Also, the function derivatives are not going to be continuous. This is what we will talk about that later, but I just wanted to highlight that here, that those are the main disadvantages of using mesh refinement. On the other side, on the P approach, or using higher order polynomial, 1 element is used for the entire domain, and the accuracy is improving significantly. But on the other side, every time that we add 1 more node, we need to reformulate, we need to recalculate everything from scratch. So obviously, this method is not best for computers because we can't reuse the elements every time. So the advantage is higher accuracy. The disadvantage is requiring the formulation again and again for every configuration. So which method is better to be used in computer programs? The H approach, in which 1 element is made once and then it is reused, is best for computer programs. By the way, we don't always use simple elements like a linear element. We can also use higher order elements. And in our course, we talk about the higher order elements as well. Okay, now let me talk about an example of application of the function approximation in the real world in the structural analysis. If you remember, at the beginning of this course, we have solved one simple problem. We have calculated the displacement field, the displacement function of this problem, a rod that was subjected to a distributed load along its length, and it was supported on the left side. We have seen that the governing differential equation is described like this, and after solving this and applying the boundary condition, the displacement function is obtained as shown here. Ux is q divided by 2ea multiplied by 2lx minus x squared. Now we want to use this function as the field function and try to approximate this at a certain point. So assume the modulus of elasticity of the rod is 25,000 megapascal, area is 420 squared millimeter, length is 3,000 millimeter, and the force acting on the rod is 7.5 kilonewton over meter. We want to approximate the value of displacement at a point located 500 millimeter from the left support. In order to solve this problem, first we need to know what are the values of the function at the beginning and at the end of the element. In other words, we need to calculate the nodal values. So I simply plug in the values here after doing the unit conversion. For instance, this 7.5 is given in kilonewton over meter. That has to be converted into newton over millimeter. The modulus of elasticity is in megapascal, so there is no unit conversion involved. Area is also given millimeter squared, so I would simply plug the value in. The length is also given in millimeter, so I plug in the value here, and the function is going to be simplified into this form. Now, in order to calculate the nodal value, we need to see how much is the value of this function at the beginning and at the end of the element, at x equal to 0 and at x equal to 3,000. And I would simply plug in the value of 0 and 3,000 into this equation in order to calculate the magnitude of displacement. So the displacement at the beginning is 0, and it is clear because it is restrained. And on the right side, the value of deformation is 3.214 millimeter. These are the only data that we need from this exact function. So given these nodal values, we want to see how much would be the approximate value of displacement at x equal to 500. In order to do that, let's start with calculating the mapping function and see what is the equivalent coordinate in the local coordinate associated with x equal to 500 millimeter. To do that, we need to define the mapping function. So the mapping function is a simply shape function multiplied by the nodal coordinates. If we write that in the matrix format, this is going to be the form. In other words, n1 multiplied by x1 plus n2 multiplied by x2. n1 was 1 over 2, 1 minus cosine, and n2 was 1 over 2, 1 plus cosine. These are the standard shape functions defined in the local coordinate. And those are going to be multiplied by the nodal coordinates, 0 and 3,000, the coordinate of the beginning and the end of this element. After simplifying the calculation, x is going to be equal to 1,500 multiplied by 1 plus cosine. Or if I want to write down cosine in terms of x, that would be equal to x divided by 1,500 minus 1. These two are the mapping function. The left one is going to give us the value in the physical coordinate in terms of the local coordinate, and the right one is going to give us the coordinate in the local coordinate system if the coordinate in the physical system is given. All right, now I want to see what is the value of cosine at x equal to 500. I would plug that into this equation, and that would give us negative 0.666. All right, now we are going to approximate the deformation function at x equal to 500. The value of approximate function at x equal to 500 in the physical coordinate is equal to the value of the approximate function in the local coordinate at point negative 0.666. Now, the approximate function is defined as the shape function multiplied by the nodal values. The shape functions are the standard shape functions that we have defined before, and those are going to be multiplied by the nodal coordinates that we have calculated before. These shape functions are going to be calculated as numbers. So I'm going to insert the value of psi into n1 and n2 and do the calculation and write down the answer here. So this is going to be the value of the approximated displacement at x equal to 500. Now let's compare that with the exact value of displacement at that point. For this problem, we already know what is the exact function for the displacement. We have calculated that before. So I'm going to plug in the value of x equal to 500 into this equation, and that would give us 0.982 millimeter. Compare these two values with each other. The approximation is not exactly similar to the exact function at that point. The accuracy of the approximation is not great. If we draw the approximate function and the exact function, this is what we would see. The value of the approximate function at x equal to 500 is 0.537, and the exact function at that point is 0.982. Comparing the approximate information and the exact information shows that the accuracy of the approximation is not great. And that is simply because we tried to approximate this curved function using a line. And it is not a surprise that a line is not capable to represent that curve function properly. But how can we increase the accuracy of the approximation for this problem? We can use the H approach or mesh refinement approach. Like, look at this one. In this example, I have used two linear elements, and as we can see, two linear elements are going to capture the shape of that function much better. We can increase the accuracy by increasing more number of nodes here. And by using more nodes and more elements, we are getting closer and closer to the exact function. That is the idea of approximation. We can get as close as we want to the exact function by using more elements in smaller mesh. Okay, with that, I conclude our discussion on the function approximation. In the next lecture, we are going to extend the concept of function approximation to approximating the derivative of a function and approximating integral of a function. I do have one assignment for you. I want you to solve this problem that I just discussed here using two linear elements. The answer should look like this. Also, I want you to solve the exact same problem using one element that has three nodes. So you need to use the second order Lagrange polynomial. I will put the problem statement on Canvas with details on what are requested for this problem. Thank you very much, and I will see you on the next lecture.